Hi, everybody, and welcome to the Reliable and Interpretable Artificial Intelligence course taught at ETH Zurich. My name is Martin Vecev, and I'm a professor at ETH. And in this lecture 8, we are going to start studying certified defenses. Certified defenses are training schemes which aim to produce neural networks that are easier to verify, easier to prove properties about than neural networks produced via standard training or via adversarial training that we looked at so far, right? So few interesting points about these lectures will be that we'll see how many of the techniques that we looked at so far in certification, zonotopes or polyhedra or boxes, right, will be used now in the context of training rather than just for the purposes of verification, right? So many of the techniques we looked at so far will actually come together a little bit in this lecture. On one side, the relaxation methods we looked at, and on the other side, the adversarial training that we studied before. Okay, so let's begin. So the main question that we want to answer here is, can certification methods benefit training, right? Can many of these techniques we looked at so far, this bound propagation, this convex relaxation, actually help with certified training, okay? Now, why are we looking at this material here? It's because at the end, what we aim to do is to produce neural networks that we can prove properties about, right? And now, it probably is somewhat obvious that if you try to verify networks, models which are not meant to be robust and just trained via standard means, will certainly be more difficult than if you try to verify networks which are specifically produced with the purpose of being more verifiable, right? Now, one point to make here is that there is a difference between training the network to be experimentally robust, like with the PGD defense that we looked at before, versus training the network to be provably robust. So training the network in a way where it can be verified with a particular certification method, let's say, right? And it is the latter that we'll be studying in this lecture here, okay? And so the question then is, can we use these certification methods that we looked at so far, all these convex relaxations, in a way where we can produce networks that are easier to prove properties about? Okay. So in some sense, an important point here is that in fact, the whole direction of verification and the methods used there are orthogonal to the training schemes that we are going to be looking at in this lecture. And so any progress that you obtain in better convex relaxations or better verification methods in general, these methods can then be used and plugged in the training schemes that we're going to be studying today. Okay. So before we start with the certified defenses, let's remind ourselves of the adversarial training of the PGD defense that we looked at in earlier lectures. And if you don't remember the PGD defense, you can just go back to some of the earlier lectures to see examples and describe the details of this training scheme, right? But this is just the optimization problem that I'm reminding you of here. So if you remember, we had two parts here. One is the, let me just take draw here, right? So one is the outer minimization problem over here, and one is the inner maximization problem over here, right? So it consisted of these two optimization problems in a sense, and they were solved in this way and approximated in a way we discussed earlier, right? So we're going to have this scheme here, and let's now see how the certified training schemes would look like. So one point to mention here with the standard adversarial training is that we're trying to find the input point here, x prime, that belongs to the input region S of x, which tries to maximize the loss. So let's see how this term is going to change when we are looking at certified training schemes. And then once we see that, we're actually going to put the two side by side to make the point even more clear. All right. So now let's take a look at how certified training would look like. All right. And so what we have here is that we have kept the auto minimization problem the same, right? The problem of finding the weights theta that minimize the following function, okay? But there is a change to the inner maximization problem. So what changed here is, the only part really that changed here was this expression over here. So instead of finding a point x prime that belongs to the region, to the input region S of x could be the, for instance, a infinity ball that you put around x, or some other region that you care to certify, right? So instead of doing that, what we do here is, and we're going to decipher this a little bit now. So we still have our, our point x here, and we have our symbolic region S of x, right, over here. Okay, so we still have that. Now, however, instead of finding a point x prime belonging to S of x, what we do is we propagate that region S of x, we propagate the region S of x through the neural network. We push it through the neural network, like this is our neural network, and the hat here stands for the fact that we just symbolically push the region S of x through the neural network. And how do we push it? Well, that's exactly the techniques that we looked at so far. It could be that we use a zonotop approximation to push S of x through to compute bounds. We can use deep poly, we can use box, we can use other relaxations that somebody comes up with in the future, but we push it through. And once we push it through, like using our standard means, we are going to obtain some region over here, some outer region here, this NN sharp S of x, right? Just going to be some convex shape, let's say. And what we're trying to do is essentially find the point Z inside this convex shape, which maximizes the loss, okay? And so essentially what we're trying to do is find the worst case behavior of the loss under this abstraction or under this relaxation that we're using to propagate the region S of x through, okay? There is no, as you see, there is not really verification going on here. We're just pushing these regions through the networks, the shapes for this S of x shape through the network, and then we end up with an outer shape, and we're trying to find a point inside that shape that maximizes the loss, right? And then we try to find parameters theta, weights of the network, which eliminate that point, let's say, that maximizes the loss. Okay, so in a very intuitive manner, you want to think of it potentially as trying to find a network which minimizes, makes the outer shape that you get from the propagation smaller. Okay, so it tries to shrink it in a sense. This gamma here, right, what this gamma is, remember we discussed it last time in the theory of abstract interpretation, which is just to be mathematically precise. It just takes your outer shape that you get here, the output shape, and concretizes it, right? It concretizes it to all of the possible concrete points that it represents. So you just get some set. We could have potentially written it without the gamma, but we write with the gamma to be more mathematically complete. And then, that's how the certified training would look like, the first kind of certified training that we're going to look at. And this general style of certified training, right, the certified training scheme was introduced in the work by Matthew Meerman, Timon Gere, and myself in ICML 2018. And there were other works in parallel who are also trying to incorporate convexity and convex information in training, but this is one kind of general way in which you can understand it and how it compares to the PGD training. Okay, so I hope that is clear. It's really just a one-line change here. Okay, but this one-line change ensures that you try to find the weights where the convex relaxation behaves well, right? Okay. And so let's see it visually, how it looks like, right? So what we have here is, again, we have the region S of x, right? This is what I explained. And we push this region through the transformers, right? This is our transformers. We get another region here, and we push it through, we get it. And this is our output region over here. This is our, this is NN sharp S of X, okay? And we're trying to find some Z here, Z inside here. Well, we should probably use red here, but we're trying to find some Z inside that region, which maximizes the loss, the particular loss that you're using, okay? And notice that one thing that happens here is that these arrows are not just your normal arrows. These are not the normal concrete behavior of the neural network. These are the abstract transformers which are used to produce these convex shapes. And so you essentially have to backpropagate through the code of these abstract transformers, right? You're trying to say, well, can you find weights in the network such that if I push my shape here, S of X, through this network with these weights, with the particular abstract transformers that I'm using, the loss behaves well on this output shape over here. So for those who want to imagine it even kind of intuitively, you're trying to potentially minimize this shape here, find ways that minimize this shape over here. But the important bit here is that now you're backpropagating, through the code of the transformers rather than through the normal, operations, normal activations and transforms of the neural network. Okay, so potentially the more complex your transformers are, the more involved the backpropagation will be. But essentially what you're doing at the high level here is you're essentially doing automatic differentiation, not on the concrete transformers, not on the concrete activations and transformations of the network, but on these abstract transformers, okay? So essentially automatic differentiation of abstract interpreters, okay? And this is why the work that we did was called differentiable abstract interpretation, because you differentiate with respect to the abstract interpreter. You're trying to find weights in the network which make the abstract interpreter produce shapes where the loss behaves, the worst case behavior of the loss in that final shape behaves well. Okay, so that's the high level idea here. All right. I hope that's clear. And so let's put the standard adversarial training and the just this here and the certified defense that we just introduced side by side so that we can imagine it. So adversarial training is something we looked at already in earlier lectures. If you don't remember, just go back to that lecture. And certified defenses is what we looked at now. And so as you see in red, I have outlined, let me just use the red here just to be consistent. In red, I have outlined, the only differences that we see between these two training schemes. So one is not training with the abstraction in mind. The adversarial training doesn't take into account any kind of relaxation or convex relaxation or abstract transformers or any of this, while the certified defenses take into account these abstract transformers, right, that you use to propagate the region through. Both of them have an outer minimization problem. Both of them have an inner maximization problem. And so the only difference is what are you doing this maximization with respect to, right? This hopefully gives you clearly what the differences are. Okay, now what I want to do here is to instantiate the general optimization problem a little bit, right? And go over how would you actually use it in practice. Okay, so this will be a little bit more involved here. So the crux of the matter here in these certified defenses is the inner optimization problem. So this is the inner optimization, the inner maximization problem, right? That we have. We're trying to find the point Z, which makes the loss behave badly, and this point Z has to lie inside the output region, output convex region. If you're using convex relaxation, if you're using non-convex relaxation, the region may be non-convex, but bottom line, you're trying to find this point Z, which makes the loss behave badly. Okay. So let's look at, before we look in the abstract, how would we instantiate this? Let's look at it in the concrete a little bit first. This is actually not computable, but it actually gives you a very good intuition here how things work. Okay. And again, a key point here is that the certified defense mechanism works with any abstract relaxation that you plug in, any of today's relaxations and any future relaxation that you define. Okay. Again, so let's look at here. So we are given the input text. So in our case, let's pick an image here. Okay, we put some region around it. Okay, like here. So we get, let's say, an infinity box around 8 with some epsilon. Okay, so let's just use the example here. And then we push this region through the neural network. Okay, and we end up with, let's say, some zonotop here. Doesn't have to be a zonotop, could be some other shape, but the original paper, the 2018 paper, instantiated this scheme with boxes and with zonotops and with variants of zonotops that scale a little bit more and combine with the box abstraction. Okay, and so if we use zonotops here and we have we have the MNIST data set, we're going to end up with 10 dimensions over here. All right, for the zonotop. And what are we going to do now with this zonotop here? I have pushed it through using standard means, using the techniques that we looked at the previous lectures. Okay, but now what I have to do is I have to compute the worst case value of the loss. I have to compute this max of L here. Essentially, I need to conceptually compute the abstract transformer for this L, given this abstract shape over here. Okay. So let's look at it, how you do it in the concrete first. So what would we do just to get an idea? So first thing we're going to do, mathematically speaking, we're going to apply the gamma. Okay, so we're going to apply the gamma. Okay, so this shape over here, where it says zonotop, is this part over here. Okay, so this is this part over here. And where it says gamma, like what? Let's use another color here just to make the point a bit clearer. Now, this part over here, this set that we get here would be this set over here. This is the gamma applied to this zonotop shape over here. So what would the gamma produce? Well, the gamma would produce many vectors here, okay, of the possible concrete values, of the Z of the zonotop. So this each entry here, okay, the Z1 has a bunch of entries, has 10 entries, right? And each of them has concrete values. The Z2 has many entries, 10 entries, and each of them has concrete values, Z3 and some Z24. I just put some number here, just to say that very large, okay? And potentially infinite here of possible concrete vectors for the Z0 to Z9, okay? So just to be clear, this Z1 is just the first vector, Z2 is like the second vector, okay? All right, so we have these vectors, and each of them has 10 dimensions, okay? And then what we do in the concrete, we will take, each of these vectors, Z1 to Z1 million, and then let's say for the Z1, we would apply the loss, right? So we'll just apply the loss over here. We'll apply the loss. And once we apply the loss, we're going to obtain a value of that loss for this concrete vector Z1, okay? Then one thing we can do is, so these are typically the logit vectors, right? Just before you apply the softmax, okay? Okay, if you have another loss function, there's different loss function. This could be the Z's after the softmax. So it depends how we instantiate it here. Okay, but for now, let's just work mathematically. So we take this, this vector Z, we apply the loss, we get a value. Okay, then we have another vector over here. So let's say this Z2, we apply the loss, again, we get a value. So we're going to get many such possible values of the loss in the concrete, right? So we do that with respect to the target label Y, okay? So as I say, I apply the L to each of the Z's, and then you would combine the result. So it could be that you compute the max, could be that you do some other operation, but you do some computation here, and then you'd end up with some value, okay? So think of it as kind of the worst case value of your loss that can be induced by looking at all of the possible concretization of this zonotop here. Now, this is just mathematically how we will do it, but in practice, we cannot actually implement the gamma, because this can generate an infinite set here. Okay, and so we cannot actually run this gamma like this. What we need to do instead is we need to have an approximation of this computation. So if you want to think of it as like max sharp, so some approximation of this concrete computation here. But the concrete computation gives you a kind of a good understanding of what this expression here gives you, right? Idealized in the ideal setting. Okay. So let's see how we would actually instantiate this scheme. So what are the parameters of this scheme? Well, one clearly is the abstraction that we use. Sharp here, maybe zonotop, maybe boxes, maybe some other relaxation. So that's one. Another parameter, to instantiate this certified defense is the particular loss function that we use. Okay, so it can be instantiated with different loss function, and we'll see a couple of those. So let's instantiate it a bit to see how to actually use this scheme. All right. Okay. So let's pick a particular loss function L. Okay, so let's pick some loss function here, and that's the loss function that we used in the original paper. Since then, we've used other loss functions like the cross entropy, but this was the one here. So this was the loss here. So this Z is a concrete vector. Y is the target label. Okay, and what we have is we are trying to find. So the loss says that we are trying to find the essentially the maximum violation from the correct prediction, Y. Okay, so we take the unnormalized probability. So this is typically applied before the softmax, so before we actually get standard probabilities. Before we get probabilities, we just do it on the unnormalized probabilities. So you would get some unnormalized probability for Y, you would get some unnormalized probability for Q, and you're trying to find that Q which maximizes this this distance over here. So tries to maximize your violation. And then what you're going to try to do with your outer optimization is try to minimize this maximal violation, if you like. Okay, so this was the loss function that we used for certified training in this original work that now has become quite popular. Okay, so now let's go back to our scheme here to see how we would instantiate it instantiate the scheme with this loss function. So as we said, remember, we cannot apply the gamma directly to compute the set of possible logits. What we need to do is, all the possible logits, we cannot do that. And so what we need to do is essentially approximate this function, this loss function L that we're showing on this slide, and compute some worst case possible value of that loss function without actually generating all the possible logit vectors, which is infeasible. Let's see how to do this. How do you actually use this in practice? Okay. So let's go back here to our scheme. So what we have is now we have picked a particular loss function to instantiate this certified defense optimization problem with. Okay, so this is the loss function that we already looked on the previous slide. All right, and again, this was the scheme that we did before, this concretization here of gamma, and that's not feasible. So we need to do something else, okay? We need to compute the worst case loss, on the zonotop, but without doing all that stuff over here, okay, without doing this. But clearly we wanted the worst case computation to be such that it that it is sound, right? We looked at before what soundness means in a way that it approximates in a sound way what this computation here would do with the concretization. That's why I showed you the concretization, so that you get into this mindset of thinking first about the concretized behavior, even though it's cannot be implemented on a computer, but mathematically you should think what it is first before you actually define the abstract transformers of this loss here applied to some, some symbolic zonotop over here. Okay, that's important, kind of thinking wise. So let's see how we'll do this. Okay, so as I mentioned already, the key problem is that the set of logit vectors could be infinite or very large, so we cannot just enumerate this, although that's the mathematical definition. So we need to approximate it, just like we did before. Every time we had any kind of infinite set, we have ways in which to approximate them with our convex relaxations that we use with abstract interpretation. So let's see how you do that here. Okay, so now we are in the abstract. Before we were in the concrete, we still need to solve the same optimization problem. We're still using this loss function, but now we need to see how to actually solve it without using this gamma. Okay, so up to here, like this part on the left is still the same. Nothing has changed. So up to here, it's all the same. So I'm obtaining this shape over here. I'm obtaining some zonotop here. Again, we're instantiating this scheme with zonotops just to give you the understanding. You can instantiate it directly with boxes. You can instantiate it with other convex relaxations, and you need to define the transformers the way we're going to do it now for this convex relaxation to compute the potentially worst case value of the loss. So let's see how to do it for zonotop here. Okay, so one thing we need to do in this loss is, you see over here, we need to compute the difference in the logits of the correct label y with all the other labels. So for every other label, we need to compute this value and then take the maximum value there. Okay, so what we're going to do here, we're just going to, we have a zonotop here, 10-dimensional zonotop. So now let's do the following. Let's compute this difference here. So this D0 is the difference between the logits, right? Logit value for label 0 and the logit value for label y. Okay, so we do this for all of the labels that we have. So we have 10 labels, so we do it for labels. Of course, one of these labels will be the y label here as well. And so we have these differences over here. Okay, so we do that. Now, when we say we compute it, I mean, that's an expression. So what this really is, what does this arrow here means? What it means is, I mean, you see here, this is an affine transformation. And we know that the affine transformation is exact in zonotop. Okay, so it's not, so we just give this expression. And, the way you may want to think of it is we're just pushing this zonotop for this expression. So push this zonotop for this expression. And, we just obtain the dimension, another dimension added to the zonotop, D0, which captures this difference. So if you like the symbolic difference between Z0 and ZY, and Z0 and ZY, it is itself some expression, some affine expression, right? 0 is here, is some affine expression, and the ZY is also some affine expression. Okay, so we do this for all of the labels that we have, and what we're going to end up with some affine expression involving error terms for D0, affine expression for the D1, right? So D1 here, we also do that, and we do the same thing for D2, D3, D4, D5, D6, D7, D8, D9, and we obtain affine expression for each of these 10 dimensions. Okay, and if we do that, and that's going to be exact because zonotop transformers for affine are exact. We looked at that before. So we're going to end up with another zonotop here. I have drawn some figure here. It's actually not a zonotop, this figure, but it's just some shape. Okay, so we're going to end up here with some other zonotop with more dimensions. We really just care about these dimensions, D0 and D9. We don't longer care about Z0, Z9, but we show them here just so that you get a bigger zonotop here. Okay, and so what do we need now? We have some symbolic expression capturing the difference here, another symbolic expression capturing the difference here. So what we want to do intuitively is take the worst case possible values for these symbolic expressions. Okay, there are a few things to be said here. Let's first see how we do it and then discuss a little bit. Okay, so let's take the expression D0. This is some affine expression here. Okay, and we're going to see on the next slide an example of this of an affine expression and how we do the maximum. So what we're going to do is first we're going to compute the box concretization of this affine expression. And remember, we already saw this before when we were discussing the ReLU transformer for zonotops, right? We had to compute the box concretization. So we do exactly the same thing here. So this box just means take the box concretization of the affine expression D0. So get rid of this error term there essentially. So let's do that. And if we do that, we'll just end up with some range for the possible values for the 0, in this case 0.1 to 0.3. Okay, and if we do that, we're just going to take the maximum of these values, because that's what we care about here. We care about the maximum. Okay, if we care about the maximum, then we take the value which is here, which is 0.3. So we're going to end up with 0.3. We do this for all of the dimensions, for all of the 10 dimensions that we have, D0 to D9. So here for D9, we just ended up with some range, some box range between minus 0.4 to minus 0.1. So the maximum would be minus 0.1. So assuming there is nothing greater here in these 10 dimensions, right, in the ranges than 0.3, when we take the max here, we're going to end up with 0.3. Okay, so what did we just see? What did we just see here? So let's just add a color. You know, what we saw here in this part over here, just like this, on this part over here, what we saw is the, you know, the abstract transformer for this loss applied to a zonotop that is no longer concrete, but it is abstract. Okay, so now here what this red thing is really, this is just L sharp. If you want to be precise, we can say that this is L sharp, which is the abstract transformer for the loss applied to some symbolic zonotop over here that we have. Okay, so obviously if you pick another loss function in the concrete, you need to define the corresponding abstract transformer for that loss, which, you know, computes the worst case possible value of the loss, you know, on this inputs in this concretization of this zonotop. Now, few things here to be one should notice is up to here, everything we did was exact, right? Because affine transformations are exact. But over here, we kind of Cartesian things away. We forgot about this part here, about the original zonotop, and we just looked at, you know, the 10 dimensions here, the differences. And so we did that. And then we not only did that, we kind of looked at them in isolation. We looked at D0 in isolation, D1 in isolation, D9 in isolation, in order to compute the box ranges. The moment we start talking about box, we look at them in isolation. So which means that this may not be the overall at the end, this may not be the optimal worst case value of the loss, but it is some approximation, right? It is some sound approximation of that. Okay, so any other value, a sound value of this that the loss can produce is going to be less than this 0.3. Okay, so there was some approximation going on over here in this part over here. Okay, approximation. Okay, so that's how when originally this method was introduced and instantiated with zonotops and this loss instantiated with zonotops, this particular loss. Okay, that's how it operated. That was its operation. Later, people instantiated it. Other researchers instantiated it with other loss functions and different relaxations, not just okay. So this gives you hopefully a good idea how to instantiate the general certified defense optimization problem with particular relaxations and loss functions. Okay. All right. Just before we move on, I'm not going to spend too much time here because we already did that in the previous lectures. This is just finding the, given the expression, in this case, expression D0, finding the interval concretization of this expression, and we already discussed how to do this. You can just make a linear pass. Here we did it in the naive enumerative way. We just plug in the values for epsilons, -1 and 1, in this D0, obtaining the different possible values that this D0 can take with the different corner points of D0 over here. So 4, 0, 6, and 2. And then, you know, the range would be 0 and 6. And so the maximum would be 6. Of course, as we discussed before, you don't do this enumerative manner, you just make a linear pass, and depending on the sign of the coefficient in front of the error term, you would pick a different value for epsilon, either -1 or 1. Okay, but that's how, just a reminder. It's mostly a reminder how to compute the interval concretization of this affine expression here. All right, so that we are more self-contained. All right. So what happened here is over the once DFI was introduced, this general training scheme, different researchers instantiated it with different loss function and with different convex relaxation, right? Trying to improve on the results. Okay. So one popular instantiation of this method and an extension was by DeepMind in this paper called Effectiveness of Interval Bound Propagation of IBP for Training Verifiably Robust Models. Okay, and what they did was, again, they instantiated the the DFI training scheme, but this time with not with zonotopes, but with simple boxes, like with intervals, as the title says, intervals, interval bound propagation, and the standard cross entropy loss. Okay, so that was good. So here is just, instead of using the loss being this maximization, worst case maximization that we looked on the previous slide, they just use the standard cross entropy loss. Now, if you have the standard cross entropy loss, remember what you need to do. You need to actually define the abstract transformer of the cross entropy loss for the particular relaxation that you're using. Now, in their case, they're using box. And so they have to define the effect of the cross entropy on box, okay, to compute the worst case value of the cross entropy. If you're using DFI with another relaxation, you'd use, you'd have to define the corresponding transformer for the cross entropy, okay? All right, so let's see a little bit, how would you instantiate the DFI training scheme with the cross entropy loss and the box relaxation, right? Okay. That's how it looks like. Let's use our notation here. So what we have here is, instead of a zonotope that you propagated, the last abstract shape, the last convex shape, is no longer a zonotope. It is a box. Okay, so this Z sharp is a box. Okay, and now you need to define the worst case value of the cross entropy for this abstract, for this hyperrectangle here, essentially. Okay, if you have a zonotope, you can, as we saw in the previous slide, you can trivially convert it to a box and apply the same scheme. So you can just take the box concretization of the zonotope and do exactly the same thing here. Or if you have deep poly, you can actually again do the same. Find the box concretization of the the interval approximation of the deep poly and apply exactly this thing that we're going to look at now. Of course, that may not be optimal, but it's one way where you can directly instantiate the scheme. Okay, so we have this hyperrectangle here. So we have essentially for every dimension. So we have, you have some Z0 over here, Z0 and Z9, ranges in this range L. Oops, I'm drawing it here a little bit. Okay. Every dimension has some range, some box, okay, signifying what the value is that this dimension can take. So now let's assume that the correct label is 4. Okay, so we're in the MNIST data set and the correct label is 4. Okay. And so what do we need to do? What are we trying to do here? What we're trying to do is find the worst case possible value for the cross entropy on any concretization that can happen here in these intervals, right? So if there is a concretization of this interval, I would just, take that concretization, apply the cross entropy, I would get a value. I have another concretization of this interval, find concrete points of the dimensions, apply the cross entropy. This, again, this gamma-based thinking that we showed before, you can do that, but that's of course mathematically possible, but it cannot be implemented. And so we're just trying to find the worst case value of the cross entropy that can be produced in these ranges that the Z sharp takes, okay? And so the rationale is going to be as follows, and that's important here. We essentially, because of the nature of the cross entropy and what the cross entropy does, what we want to do is to find the worst case possible values of the dimensions which are not the dimension of the correct label. Okay, so if y is 4, okay, if y is 4, then what we're going to do, so I is 4, so y is 4, so this is going to be 4 here. Okay, if y is 4, we're going to pick the smallest value for this dimension. So we're going to pick L4, okay? For any other dimension here, we're going to pick the highest possible value. Okay, we're going to pick the highest possible value. So if y is 4, we're just going to end up all here on the right. We're going to end up with U0, U1, U2, U3, and here we end up with L4, okay? For the dimension that we care about, for the fourth dimension, because y is 4, and for all the others, we pick the highest value. Why do we do such a thing? Because if we do that, right, and we apply the softmax after this, on this logit vector here, okay, the smaller the value for this Z4 is, this is Z4, dimension Z4, the smaller the value here is, and the larger the values are for the other dimensions here, Z0, Z1, Z2, Z3, right? Then once we apply softmax to this this vector over here, right? What's going to happen is you're going to get the worst possible values for the cross entropy, right? You're going to get the smallest possible value here for L4 prime. So the larger the values here are, just take the larger the values here are, and the smaller the value L4 is, when you apply the softmax to this, you're going to end up with smaller and smaller L4 prime, okay? And so that's what you want to do. You want to pick the worst case behavior for the other dimensions, maximize those, while minimizing the values for that Z4 can take. And we know the ranges, so we know that the other dimensions cannot go above these ranges, U0, U1, so we just take those values. And for the fourth dimension, we take the L4, which is the smallest possible value, okay? And so then once you apply the softmax, you are going to end up with the smallest possible value here of L prime, L4 prime. And then the rationale here is that when you apply this to the smallest possible value, you're going to end up with a larger value for the cross entropy. So remember, you're trying to maximize the cross entropy, trying to find the worst possible value of the cross entropy here, okay? So the larger these values here are, and the smaller this, this value for Z4 is, once you apply the softmax and after that you apply the cross entropy, the larger this value of the cross entropy will be. So this gives you essentially the worst case behavior of the cross entropy loss by doing this kind of, so let's see, this is essentially over here, the abstract transformer, okay? So what we do essentially, we compute, given the intervals here, we find a concrete vector here, and then on that vector we apply the softmax, and once we apply the softmax, on that we apply the cross entropy, normal cross entropy loss. So really the key step is over here, the first step, okay? So that's how you can actually instantiate the this dphi scheme with the cross entropy loss and the box relaxation. If you don't have the box relaxation, you can just take the interval concretization of the particular relaxation to again end up with this scheme over here. All right, so that's how the DeepMind paper instantiated the dphi setup and improved on some of the results there. Okay, so there is some additional tricks that the IBP, the DeepMind paper, had at that time. So one idea here, we're not going to spend too much time here. So one point here is that rather than starting with the entire region S of X, you start with a small region around X, okay, some small epsilon, and you gradually grow this region during training. Okay, so the rationale behind this is that if you start with the entire region, your network may still not be ready, okay, and you may generate a lot of garbage points because you are considering, your weights are still not ready in a sense. You're propagating the entire region S of X, but by starting with smaller and smaller regions, you would, gradually tilt the weights towards being able to handle the larger region. Okay, so this is a heuristic that turns out to be useful in practice in producing better results in accuracy and certifiability. Okay? All right. Now, even though the whole propagation in this work was done box using simple intervals, actually in the last layer, that work found that handling the last layer precisely is important. So the last linear layer is handled exactly, essentially via zonotops. Okay, it's not called zonotop in the paper, but that's what it is. And then another point here is that there's a parameter that dynamically weighs the cross entropy loss with the correctness cross entropy loss. So you typically in this kind of certified training schemes, you have the certified loss, which is the maximal loss we showed before, or this particular cross entropy that we looked on the previous slide. But you just have the normal loss that you use for accuracy, and then you weigh the two, find a parameter that weighs the two appropriately. Okay. Now, since then, a lot of these tricks and different relaxations, combinations with zonotops that scale to larger networks and dynamically concretize to box, and various other training, tricks that you use to get the results higher, has been implemented in the DeFi training system, DeFi 2.0. So you can take it, you can play with it, right? And see how there is actually a domain-specific language there, which lets you specify the different parameters of training. Take a look. But what I showed you before is pretty much the core, of the whole differentiable abstract interpretation, certified training method. The optimization problem that I showed you is exactly the same. It's just instantiated with different loss functions, with different relaxations, and with different tricks and hyperparameters that are used to improve the results. Okay. Right. So hopefully this gives you a good idea how these certified training schemes work. Now, since DeFi was introduced a couple of years ago, various groups have used it and companies to produce more certified networks, and we've also used it. Now, there's several points to be made just coming from a practical standpoint that are actually important and motivate other certified training schemes that we're going to be looking at next. Right. So first of all, boxes, intervals scale to large networks. Okay. Now the problem is with them is, as you expect, they're quite imprecise. So they introduce, we already discussed this before, they introduced a lot of invisible points in this output shape that we looked at, okay? So this means that the deeper the neural network is, so the deeper you go, the more layers you have, the more this capacity increases. So, potential for higher accuracy goes up intuitively, but the more we are training with respect to labels, okay, to these garbage points, to these points that actually can never happen if we actually look at the concretization of the input box and run it through, okay? So we're going to be accumulating a lot of invisible points and training with respect to this, right? Because remember, we're trying in our optimization problem here, we're trying to find this Z, this point, which belongs to your output region that maximizes the loss. But this point Z may actually be quite invisible, okay? And so if you train with box, if you instantiate this, DeFi training scheme, this optimization problem with box, whatever loss you're using, the accuracy tends to drop quite substantially of the resulting network. So the standard accuracy drops. Okay? Of course, certifiability, provability improves. You can prove more things. You can prove more images robust, but your accuracy goes down. Okay, we already saw this phenomenon before when we looked at adversarial training, where we said that accuracy goes down, but the network is more experimentally adversarially robust. So same thing here. Now, how would you address this point, this issue, this challenge over here? The fact that you are getting a lot of invisible points and you're training with respect to this. Well, naturally, what you do is you'd say, well, let me use more precise relaxations like the zonotop relaxation or the deep poly relaxation or some other relaxation. Now, what happened was, what's interesting is that, and this is all empirically speaking, it turned out that generally more precise relaxations, like zonotop, for instance, when you instantiate these DeFi training schemes, actually can lead to worse results than box. Okay, so now that is quite interesting. So you get worse results than box. You may get worse accuracy or worse probability, but uniformly the results do not improve. So you would expect to get better accuracy and expect better standard accuracy and more probability, but that's not what happens. So that's kind of quite an intuitive, right? In verification, when you select more precise relaxations, you are able to prove more. But when you use these more precise relaxations during training, it turns out that this may actually not be the case in practice. Okay, so this is unintuitive in a sense, pathological situation where more precise relaxation during training may not actually bring, sometimes they may, but often they may not bring better results in provability. And one thing you may do, and what many people did, and we also tried doing, is you start tweaking the loss, you start tweaking the hyperparameters, and this can help a little bit. But fundamentally, it is not reliable to work in this way. Okay. And so there are multiple questions that one can ask here. So the first question is, if the training with boxes has been found to be effective like this, or is it the case? So what is the promise of just using box for training? Okay, because if box works, that's great. It's very easy to train with it. It's very cheap. So why not we just use only box? Okay. So the first question we want to answer here is, okay, it's a simple question. So is there a network, is there a model, is there a neural network with perfect accuracy? So the accuracy doesn't drop, okay? So perfect accuracy, such that when we analyze this network with box, we do not lose any precision. So the way you can reformulate this question is, can I find weights in the network such that when I push the box through this S of X region for the network, at the end, when I get my output shape, my output hyperrectangle, this hyperrectangle is exact. In other words, if I had used, for instance, the mixed integer linear programming, I would get exactly the same hyperrectangle as I do with box. Now that's kind of weird, right? We know that box is not as precise as MILP, it's an incomplete method, but there may be weights that you can find where the two methods are actually the same. They give you the same, they don't lose precision. Okay, and you get the same, you get the perfect accuracy. So is there such a network, right? And so we investigated this question, okay? And the answer to this question is yes. You can actually prove that the answer is yes. So there's a work this year in ICLR called Universal Approximation with Certified Networks. Essentially what it is the Universal Approximation theorem, but this time with a network, right, which is provable, with a provable network. So you don't just ask whether a network exists with perfect accuracy that approximates a function, but you ask whether such a network is also provable with box. It is exact. Okay. So the answer is yes. Now, well, that's interesting. Oh, this sounds like we can just use box for training and we get great results. But the problem is, of course, that this is in theory. This answers these existence questions, but the construction here is still impractical, right? How you construct this network. So clearly, in practice, when you use normal networks, right? This is not happening, but such a network exists, and it's an interesting direction, and more work is needed towards studying this question with different relaxations, with different constructions, different properties that you're proving, and so on and so forth. But that's like an interesting first step in the theoretical direction. Okay. Now, but still, if you look at the second point here, which is that why are we in practice not obtaining better probability, better accuracy result if we select a more precise convex relaxation like zonotop over box. Why is that? Why is that not happening, right? So this is the second fundamental question, which is why are better relaxations not guaranteed to produce better results in accuracy and probability, right? And then just to remark, this question one, the answer, the universal approximation paper that I just shared with you, that's not something that you need to study. It's just for your own information if you want to dig deeper into this. And so the answer to this question two is actually quite interesting, okay? And here is a hypothesis that we had when we were, suffering and trying to get the results better with the DFI optimization problem, right? And the hypothesis is actually quite simple. It is that more complex abstractions, more complex relaxations, okay, like zonotop, like deep poly, than box, lead to more difficult optimization problems. Because remember, we are backpropagating through the code, if you like, of the abstract transformers. So the more complex they are, the more complex these transformers, the more complex the shapes are, the more difficult the optimization problem becomes. Okay, why is that? Well, intuitively, it's because in your network, in your neural network, we have a bunch of weights, okay? And using these weights, right, you are trying to control the relaxation, like a zonotop or a deep poly, with many more parameters than the weights. So, right, so for instance, if you look at the zonotop, you have these error terms, and these error terms accumulate, if you remember, when you have these crossing values. And so the error terms are accumulating, you get lots and lots of error terms, and you're trying to control these coefficients in front of the error terms, in a sense, by just varying the weights in the network. So you're trying to find weights in the network, which, let's say, produce smaller zonotops. So kind of this indirect way, which is quite unlike normal training, okay? So essentially you have weights in the network and you have, weights in the zonotop, these coefficients there that you're trying to figure out, okay? And this is actually quite difficult. So the optimization problem becomes more complex. The more complex the relaxation is, because it can express more complicated shapes. So it could be the case, it is such a complex optimization problem that the result actually exists, right? The network, which gives you good accuracy and probability, is there, but your optimizer has a hard time finding it because the optimization problem is so complex, okay? So it's interesting that now you get a new class kind of optimization problems dictated by the convex relaxation. And of course, there are all kinds of open questions here. How do the optimization differ with the different convex relaxations that you instantiate? That's an area that we're actually looking at actively. It's quite an interesting direction to be studying. But the bottom line out of this is that fundamentally we need a training method that, or an optimization problem, right? That the training method produces a simpler optimization problem. Okay, not the one that we looked at so far, right? This certified defenses DFI optimization problem. So we need to be looking at a simpler optimization problem, preferably one where we are not differentiating through the transformers. Okay. And so let me remind you here where we are, just to pop up before we look at this new optimization problem for certified training. So on the left we have the just a reminder. On the left we have the adversarial training. On the right we have this optimization problem for certified training. Okay, and I've added these points over here. These are generally true in practice. Oh, let me use another color maybe because we already have green and red. So what happens with adversarial training? It gets good accuracy. Maybe it drops the accuracy a bit from the standard training. Okay, you guess better accuracy in the certified training. You get, but you get worse probability. You can prove, fewer images robust, if you like. It's kind of intuitive because you're not training them to be probably robust, just experimentally robust. And this actually generates you an easier optimization problem, okay, than the certified training, because you don't worry here in adversarial training about any of these relaxations or transformers, any of that. Now with the certified training, you get worse accuracy than the adversarial training, so worse standard accuracy, You get better verifiability. You can verify more images robust, let's say. But unfortunately, the optimization problem is harder because of these troubles here, okay, because of this having to take into account the abstract transformers and the shapes themselves, right? And so the question is, I mean, when you look at it side by side like that, how can you take the best of all worlds? How can you take, take the good accuracy and the good verifiability and the easier optimization, but still having this certified training going on, okay? And so this motivates our new certified training schemes, which actually bridges the gap between these two methods, the adversarial, the experimental adversarial training, and the certified training, okay? So now let's look at this technique. So that's a technique for training provable neural networks, which we introduced this year, a few months ago. It was actually an oral paper at ICLR. Okay, and it's called CODE. And so this CODE system stands for convex layer-wise adversarial training. We'll see why in a second, but essentially what it does is exactly what I said on the previous slide. It tries to bridge adversarial training, the good parts of adversarial training, in particular the simpler optimization problem, and certified training, right? The provable defenses, the certified defenses, by taking into account the convex relaxations, all right? And so let's look at this optimization a little bit, and I think it will become quite clear what's happening. So let's look at it in this way. First, let's look at the picture over here before we look at the key challenges and the optimization problem. So what we're going to be doing at a very high level, so look at this here, at a very high level, what we're going to be doing, we're going to be doing adversarial training, PGD training, but with not just shapes that you have in the beginning over here, but with shapes that arise in the middle of the network. So the way you may want to think of it, one way is you do adversarial training, but with shapes that happen in the middle of the network, not just with the input shape. And that's the high level view of this, okay? So let's see how that would work. Well, what we'll do is the following. Again, we have our image 8. Again, we take the input S of X. This is the region S of X here that we get, okay, some region. And we're trying to do our code training, okay? And as the title says, it's going to be layer by layer. So what we're going to do is first, we are going to take this box over here, and we're going to propagate this box through the first layer, for the first hidden layer, H1. We propagate it through this layer, whatever this layer is. And once we do that, we get the following shape. This could be a zonotop, could be a polyhedra, could be whatever convex relaxation that you care about. Now, what do we do here? Well, in the normal DeFi style, we would propagate the shape all the way to the end and get over here and do our training with respect to that shape, but not with code. So what we do with code is we're going to ask the following question. Can you find a point, this point over here, okay, can you find a point inside this shape which tries to maximize the loss, tries to maximize the worst case behavior of the loss, okay? And then let's minimize this worst case behavior of the loss. So what happens here is that we find a point, X, can you find a point X1, which when you actually run this point at X1 through the network, so we take the point X1 over here, we apply H2, this is all in the concrete, nothing in the abstract. We apply H3 and we get a point X3, okay? And for this point X3, we get our loss, just like normal, okay? And now we're just trying to find the point that maximizes the worst case behavior of the loss. So let's say we find such a point X1. Once we find such a point X1, our goal will be to do what? To find weights, theta, so find weights over here for these layers H2, H3, which minimizes this loss, okay? And so we're going to essentially take this point over here, this x1, and try to find values here for H2, H3, trying to find weights that minimize the worst case behavior of the loss. So we try to mitigate the effect of this point by just changing the follow-up layers, H2, H3. We're not touching the layer H1 anymore. So you find the point, find that it gives you worst case value of the loss, and then you try to mitigate this effect of this red point, X1, on the loss, okay? And so what you would end up doing is you would end up doing adversarial training on this part of the network. You're going to be iterating here and finding weights for these layers, which minimizes the worst case, this X1. And that's what our optimization problem says. For our, so I have just instantiated it for this network. You can write it more generally, right? But there's no need to introduce additional clutter. So we just have 3 layers here, H1, H2, H3. We are at after layer 1, okay, just after layer 1, okay. So just, find the worst case value of the loss here, okay, find the point that gives, find the worst case value of the loss, and then train. Again, we have this adversarial training, find, with respect to this worst case value of the loss, find the weights theta. So this theta would be H2 and H3 in this case, okay? And so this is how this code works. So once you do this H2, H3, you have found weights that mitigate this worst case value of the loss. You have minimized the loss as much as you can, given this shape over here. And once you're satisfied with this, you move on to the next layer. So you freeze this layer, and we move to the next layer. So what we are going to do, we are going to, let's get rid of the red now, just not pollute our picture. Okay. What we're going to do, we're going to push this region over here. We're going to push it. Okay, we're going to push it, and we're going to get this shape over here. So the shapes that you see here, initially we don't have them. Initially we don't have these shapes. Okay, we just have the shape over here, and we train with respect to that. Once we are done training with respect to that shape, we push that shape through. Let me just get rid of this. We push that shape through, and we obtain this shape over here. Okay, so we obtain this shape over here, and we have at that point, once we have pushed this shape S1 through H2, we freeze H2. So H2 is frozen. You don't touch H2 anymore. H1, H2 are both frozen. So that's great. H2 is frozen. And again, you train with respect to some point over here. Okay, train with respect to some point over here. You try to find the worst case value of the loss with respect to that point. And so you, again, once you do that, you're only going to be allowed to change H3. You're going to try to mitigate the worst case value of the loss. And right, this H2, and then you finish that and you move to the next layer. So that's why it's called the convex layer once adversarial training, because you obtain a shape here, okay? You try to find the worst case value of the loss with respect to this shape. You mitigate this worst case value of the loss by finding weights for H2, H3. Then you're done. Then you move to the next layer. You go to the pass it through H2, this shape S1. And again, you do adversarial training with respect to this shape S2, and you're only allowed to change H3. Okay, so you get into this mitigation mindset. You try to mitigate the worst case effect that this shape can possibly introduce downstream in the network. Okay, so there are a few important points here with the let me just clear these drawings, with this code training. As you can see, this optimization problem here doesn't have anything to do with abstract transformers, right? It doesn't have this NN sharp anymore anywhere here. I have obtained my shape, and I'm training with respect to that shape over here. Okay, I no longer need to care about differentiating for any transformer. So this generates a simpler optimization problem. Okay, right. So that's key point one. That's something that we wanted to do. So essentially PhD training on shapes that happen inside the network. by the particular convex relaxation that you're using. Now, as we know, as we discussed before, a key challenge when you're dealing with this PGD training, with adversarial training, is projections. Before, if you're doing just L infinity boxes, you're projecting on these L infinity boxes, and that's easy, right? But if you are having these complex shapes now that arise in the middle of the network, and you're doing adversarial training here, you have to find points inside this region, right? And so you need to, if you're outside the region during your adversarial training, you need to get back inside or on the surface of the region here. And so you have to do that. So you need to do projection, find the nearest point in the region here. Okay. And so this brings the question: how do you do projections on these convex shapes that you're using? Right. So if you use zonotop, you need to be projecting on the zonotop. If you have deep poly, you need to be projecting on that. So we have shifted the complexity a little bit in these projections. Okay. All right. And projecting onto different kinds of convex shapes is actually not a well-studied problem. And one can explain potentially why. What are the efficient projections that you can obtain for different kinds of convex relaxation? That hasn't been studied that well. And why is that the case? Well, because this kind of certified training really hasn't taken place until just the last couple of years. So now let's look at projections. Originally, when we did this work, we instantiated again with zonotops, right? Other instantiations are possible that haven't been investigated yet, but we need to see how to actually project onto zonotops in order to use this method, right? In the previous DFAI method, we actually didn't have to do any kind of projections, but here we need to do a projection. So we pay a little bit of price for making the optimization problem much simpler, not dependent on the abstract transformers, that now you actually need to project onto this complex shape. So let's see how we do that. So if you instantiate this training scheme, this new code method with zonotop, you need to find a way to project. So now let's look at this slide a little bit in this order. Okay. So right, this is ultimately the optimization problem that you want to solve. You want to find the maximum value. Z is some zonotop, right? Z is some zonotop. You try to find the maximum value of the loss. Try to find a point that gives you the maximum value of the loss. And to do that, you need to do projections, okay? And so one thing we're going to do here is we're going to change the problem of projecting onto a zonotop into a problem of projecting onto a box, okay? By just doing standard change of variables. And so just a reminder what the zonotop is, zonotop is just a matrix times some, times this, a vector of possible values for the error terms where each entry lies in the range -1 to 1. And so every point inside the zonotop, right? If I have a zonotop, has a corresponding value for the error terms, okay? Such that if I plug in these error terms here in this expression, okay? So the A is the coefficients of the error terms. So A is the coefficients that we have in front of the error terms, and E is the particular error term that we picked, particular vector instantiation of error terms. We're going to end up with just a value and just a point inside the zonotop. So for every point inside the zonotop, there is a corresponding error terms which you instantiate in order to get that point. That's clear just from the definition of the zonotop. Okay. And so what do we get here? So let's go back up here in our picture. Okay, so we're over here now. So what we have is we have a point x prime in red here, which is potentially outside the zonotop, and we want to project it, this big pi here, project x prime onto the zonotop over here. And so the way we're going to do this is we're going to do it in few steps. So this is just some example of a zonotop here, x1 prime and x2 prime. So what we're going to do here is we are going to do the following. So from this concrete value of x prime, so we have a concrete value of x prime, okay, and we have the definition of the zonotop over here. From here, we can determine the values of E1 and E2, which give rise to this point x prime. So these particular values of E1 and E2, which give, which when you plug them in, give you the value of, give you the point x prime. Okay, so x prime is just the values for x1 prime and x2 prime. So we're just going to find some values for x1 prime and some values for x2 prime, some value for x1 prime and another value for x2 prime. And so we're going to find particular values for E1 and E2. Just put them here. Okay, that when you plug them in this equation here, give you the value of x prime. So that's step one. Okay. Now, once you have the particular values for x prime, the E1 and E2, the particular values for that, you can project those values, E1 and E2, you can project them, over here, there's going to be some values, you're going to project them just like you do with a normal box projection. So you're going to project E1 separately, then you're going to project E2, and you're going to, so this is minus 1 and 1 here, because that's what E2 ranges over. It's minus 1 and 1, okay, over here. We're going to project it on this box with the minus 1 and 1. Okay, this here. And you're going to end up with some values for E1 and E2, okay, in this point over here, once you project it. Okay, so once you end up with these values for this pi E, once you obtain some values for the projected E, okay, some values for E1, E2, you can just plug them in back in the equation over here, and you're going to end up with some values for x1 prime and x2 prime, which are going to give you this projected point over here. That is inside the zonotop, right? Because we know that E1 and E2 are in the range minus 1 and 1. So we know that these projected values of E1 and E2 are going to be in that range, just because we project them to that range. Then when we plug in those values inside this equation here, okay, this equation here in the middle, we are going to end up with values for projected value of x prime, okay? And so that's how the projection works in this with zonotops. Now, it's a good exercise here to see that this actually may not be optimal, right? So let me just clear the drawings here, okay? That if you do this kind of projection, you go from x prime, you go to E, you project E, you go down this way, then you plug it in, and of course, like to get this E, we had to use these equations here, right? To use these equations. And you get this PE, and then you plug it in over here, and then you obtain your value here, in this roundabout way of projecting, just because it's easier to project on the box. This way may actually not give you the optimal projection in terms of distance to the on the zonotop. So you may get potentially not the optimal results here, but it is still sound. It's still something inside the zonotop, but just may not be the closest point to x prime. So that's a good exercise for you to play with why that's not the case and find a counterexample. Okay, but it is sound again that you end up with a point which is inside the zonotop, and that's something we care about. Okay, so as you see, when you're doing this kind of projections, here we just went back to box. If you're doing this kind of projections, it's actually an interesting research direction to be thinking of good projections onto zonotops and different kind of convex relaxations, of which there is an infinite number, right? And how the projection complexity gets affected here, right? So code was instantiated with zonotops and projections just the way I showed you. You can actually play with code and see if you can instantiate with other projections in order to get the accuracy and the results of the methods potentially higher. It's an interesting direction, okay? Now this code with the simpler optimization problem and projection actually on certain data sets like the CFAR and 2 out of 255 epsilons obtained much better results than any of the other methods that were using many more GPUs and tweaking of the losses and so on and so forth. So that's quite promising direction, I would say, in terms of training probably robust neural networks. Okay. Code is public on GitHub, and you can take a look and play with it. Okay, so what we did in this lecture. So we looked at certified defenses, right? We looked at these provable training schemes, which aim to use relaxations, convex relaxations typically during training, right? To incorporate it in the training process, so to obtain networks which are more provable, networks for which you can prove, let's say, more images robust, or whatever property is it that you care about, okay? And towards that, we introduced two different training schemes, each of which corresponds to two different optimization problems. So first, we discussed this general differentiable abstract interpretation method, which comes with its own optimization problem, right? And we showed how this optimization problem differs from the standard adversarial training optimization problem. And we showed how to instantiate this method with two loss functions and two relaxations. So with the zonotop relaxation and this maximum margin loss, and with the cross entropy loss and the box relaxation. So two different instantiations has been instantiated and improved on by various researchers and companies, but pretty much the optimization problem is as I showed you, okay? Now, the problem with this optimization problem with the DiffAI is that it gets quite complex because you're trying to control complex relaxations with this small number of weights, let's say, in the network. So that's one hypothesis. And it makes it difficult to actually get the potential to reach the potential that these convex relaxations are offering you, because the more complex the relaxation, the more complex the corresponding optimization problem is. Okay. And so this triggered this study into other certified training schemes which produce simpler optimization problems, okay, that allow you to plug in more precise convex relaxations and obtain better results in standard accuracy and probability, right? And this was one of these methods called code that we introduced. This is a fundamentally new method, the convex layer-wise relaxation training, which is a certified training method that combines essentially the best of adversarial training and relaxations, right? Still uses these convex relaxations to produce a simpler optimization problem. But if you are using this method, you need to worry about projections. So you need to have good projections onto the particular convex relaxations or whatever relaxations is that you are instantiating it with, which is an interesting research directions here. Okay. And this code method reached state-of-the-art results on several data sets, in particular the CIFAR-10 data set. So it's quite promising in terms of the method to use for certified training. Okay. So I hope that you enjoyed the lecture and you understood a little bit more how certified training works. It really is a combination between some form of adversarial training and convex relaxation. So thank you, and see you next time.